Hey everyone, I'm Philip Walton, and today we're going to be doing a deep dive into optimizing LCP. But first, I want to quickly recap what LCP is and explain why I think it's so important for developers to fully understand this metric and know how to improve their scores. LCP stands for Largest Contentful Paint. It's one of the three core web vitals metrics, and it represents the time from when the user starts loading a web page until the moment when the largest image or text block within the viewport finishes rendering. At Google, we recommend that developers aim for an LCP of 2.5 seconds or less for at least 75% of all page visits. In other words, if 75% of the time your pages can render the largest image or text block within 2.5 seconds, then we would classify those pages as providing a good loading experience. But I know that sometimes that whole 75th percentile bit can be confusing, so let's take a closer look at exactly what that means. Here is an example distribution of all visits to a particular page sorted in order of LCP times from fastest to slowest. In this chart, each bar represents a single loading experience of a real person visiting this page. On most sites, you'd probably have thousands or millions of bars, but for the purposes of making it easy to visualize, I'm showing an example page that only has 36 visits. So to get the 75th percentile from a list of sorted values like this one, all you have to do is take the value that is 75% or 3/4 of the way through the list. In this example of 36 data points, the 75th percentile corresponds to the 27th value in the list, which here is just under 3 seconds, so it's classified as needs improvement. Remember that to be classified as good, an LCP value must be 2.5 seconds or less. But anyway, the main reason I'm showing this to you, this distribution of real user values, is I want you to take a look at what happens if we were to implement a performance optimization that would make all of the already fast LCP experiences even faster. Did you notice that even though the LCP times improved for these users, the 75th percentile did not change? Similarly, if the site were to improve the poor experiences so that they were slightly faster, though still poor, it would also not change the 75th percentile. If you want to improve your LCP scores at the 75th percentile, the only way to do that is to improve the experience for enough users so that at least 75% of them are within that good threshold. And generally speaking, the best way to do that is to make optimizations that improve the experience across the board, not just targeting a specific set of users. Of course, you can make optimizations that target specific users if you notice specific problems, but in this talk, I'm going to focus on general LCP best practices that apply to all types of situations. So I've covered what LCP is, as well as how you should approach optimizing it for a broad spectrum of users. But another important topic is why I'm focusing on just LCP in this talk today, instead of the other core web vitals metrics. Well, based on data from the Chrome User Experience Report, of the three core web vitals metrics, LCP is the one that sites struggle with the most. Only 52.7% of sites meet the good LCP threshold, compared to much higher rates for CLS and FID. Moreover, LCP is increasing at a slower pace than the other metrics, which also suggests that developers are having more trouble optimizing for it. We know that sites are definitely trying to improve their core web vitals scores because we've seen lots of improvement in CLS over the past few months. But clearly LCP is giving developers a bit more trouble. So this raises the question, what makes LCP so hard to optimize? I'm sure there are many reasons for this, but I suspect that a big reason is that there are just so many things to think about when optimizing load performance. And I know from talking to developers that in many cases, they're trying really hard to optimize LCP, but the things that they're trying just aren't working or they aren't helping very much. They can't figure out what they need to do that will actually make a difference for their specific site. So LCP is a big, complex problem. But I find that when you're facing a big problem that's hard to solve, it's helpful if you first break it down into smaller, more manageable problems and address each of those separately. And I think we can do exactly that with LCP. So in the rest of this talk, I'm going to present a framework for how I recommend that developers approach improving LCP on their sites. Okay, here we have an example waterfall from a pretty typical page load containing CSS, JavaScript, and image resources. And while all of these network requests are important in general, for the sake of optimizing LCP, you really only need to be focusing on two: the HTML document, and then whatever other resource may be needed to render the LCP element. In this case, the LCP element is an image, but the same principle would apply for a text node that needed to load a web font before it could render. So now that we've identified the two most important resources, we can use the relevant timing attributes of those resources to break down LCP into its most important subparts. The first subpart is the time from when the user initiates loading of the page until when the browser receives the first byte of the HTML document response. This is commonly referred to as time to first byte, or TTFB. The reason this time is important is it represents the first moment that the browser is able to start discovering additional resources that are needed to render the page, including the resource needed to render the LCP element, which we'll get to in a bit. The second subpart is the LCP resource load delay. This is the delta between TTFB and when the browser starts loading the resource needed for LCP. In some cases, the LCP element can be rendered without loading any additional resources, like if the LCP element is a text node using a system font, and for those pages, the resource load delay is 0. In general, you want your resource load delay to be as small as possible. The third subpart is the time it takes to load the LCP resource itself. Again, if the LCP element on your page doesn't require a resource request, then this time will also be 0. And lastly, the fourth subpart of LCP is the element render delay. This is the time from the moment your LCP resource finishes loading until it's actually rendered to the screen. So every single page can have its LCP value broken down into these four subparts. There's no overlap or gaps in between them, and collectively, they add up to the full LCP time. To illustrate that point, let's take a look at what happens if we were to reduce the resource load time part in this example. In this case, when we reduced the network load time, the element render delay got extended by the exact same amount of time. The time just shifts from one part to a different part, and so LCP doesn't change. That's because in this example, the page needs to wait for the JavaScript, those yellow bars at the bottom, to finish loading, since here the JavaScript is responsible for adding the LCP element to the page. So I want to pause here for a moment and really emphasize that last point, because I think this is where a lot of developers get frustrated. When they search for posts online telling them how to improve their LCP, one of the most common pieces of advice is to optimize their images. But optimizing your images will only affect this one part of LCP. And if this part isn't your bottleneck, then reducing it won't help you improve your score, as demonstrated in this example. So the key to improving LCP is to figure out where your bottlenecks are. And a good way to do that is to understand what the ideal or recommended values are for each of these LCP subparts that I've just introduced. And at a high level, the advice is pretty simple. You want to be spending the bulk of your time making network requests that are needed to render the LCP element. And you want to minimize all other time as much as possible. Anything that gets in the way of your page starting to load the LCP resource as soon as possible, or rendering the LCP element as soon as that resource is done loading, is essentially wasted time. So it's important to eliminate those times if you can. So given that general principle, this is roughly how these LCP subparts should break down on a well-optimized page. The total time in the right column is based on the goal of 2.5 seconds for LCP, and the other times are just a percentage of that. So notice how about 80% of the time is allocated to making network requests, and 20% of the time is allocated to everything else. Later in the talk, I'll walk through an example of a real-world performance optimization, and I'll use this 80-20 principle to identify opportunities to improve. And speaking of opportunities to improve, I bet you're probably curious to know what the breakdown of time spent in each LCP subpart looks like for sites in the real world. So unfortunately, we don't have real user data for these specific metrics yet, but we do have lab data from HTTP Archive, and that can give us some insight into answering this question. Here is a chart that shows the breakdown of LCP subpart timings from 5.3 million web page test runs, which is every single page in HTTP Archive where the LCP element was an image with a URL source. To make this chart, I took all of those runs and sorted the results by LCP value from fastest to slowest. And then I broke it down into 5 buckets, where the top bucket represents the fastest 20% of web pages, and the bottom bucket represents the slowest 20%. Within each bucket, I took the average LCP subpart time value to create each stacked bar, and so that the total bar length is the average LCP value within that bucket. And while this chart shows the absolute timings for each subpart, and you can visually see how the total time spent in each part gets worse as you move from bucket to bucket, I actually think a more interesting way to visualize this same data is to look at each subpart as a percentage of the total LCP time. So here's what that looks like. And to be honest, when I first looked at this data, I was pretty surprised at the results. I was expecting that the majority of the LCP time would be spent loading large, unoptimized images. In other words, I was expecting the green bars to be a lot wider, especially in the bottom row. But this data suggests that image load times might not actually be the main bottleneck for LCP on the web. From the amount of purple I'm seeing in these results, it seems like the biggest bottleneck might actually be resource load delay. Now, I want to stress that this is lab data from web page test runs. It's not real user data from the wild. This data uses a single network and device configuration for every run, so it's definitely not representative of the myriad of devices and networks used in the real world. Also, the web page test runs used by HTTP Archive don't contain repeat visits, so things like the user's cache state are not factored into this at all. So I don't think we can say with any certainty that this is exactly how LCP breakdowns look in the real world. But what I think we can say with high confidence is that sites are definitely not optimizing LCP resource load as effectively as they could be. And while that's obviously a bummer for people like me, I do think there's reason to be optimistic about the data. The subparts of LCP that are hardest to improve are represented here by the blue and green segments in the chart above. And the parts of LCP that are easiest to improve, in my opinion, are represented by the purple and yellow segments. Given how much purple and yellow we see in this chart, I'm hopeful that if we can do a better job of helping developers discover where their bottlenecks are, then we should be able to see some big improvements. So I know I shared a lot of information so far, and I haven't really given any advice yet. So let's do that now. Here is a step-by-step approach, a recipe if you will, for how to optimize LCP on any given page. There are only 4 steps, and I put them in order with the easiest and most high-impact optimizations first. Step 1. Eliminate unnecessary resource load delay. The key point in this step is to ensure that the LCP resource is prioritized so it can start loading immediately after the HTML document is received. And the best way to check on your pages whether the LCP resource is loading early enough is to compare its request start time with the start time of the first subresource loaded by the page. In this case, the first subresource is a style sheet, and it starts loading quite a bit before the LCP image resource starts. So that's a signal that there's opportunity to improve. To fix this, we could use preload or add priority hints to the image tag, and then the browser would know to start loading it earlier. You also want to check to make sure that the LCP image isn't being lazy loaded, because that will result in additional resource load delay that you never want for your LCP image. In this case, preloading the image should do the trick, and here's what that looks like after it's been implemented. Now you can see that the image resource has started loading at the same time as the first style sheet, which is exactly what we want, and so step 1 is pretty much done. But before we move on to the next step, I want to once again point out that reducing the resource load delay here did not change LCP. That is still blocked on the JavaScript code, as I mentioned earlier. Step 2 is to eliminate unnecessary element render delay. In other words, we need to make sure that as soon as the LCP resource finishes loading, nothing else on the page is preventing it from rendering right away. That can be things like render blocking style sheets and JavaScript files. It could also be something like an A/B test runner that is intentionally hiding content until it can figure out what experiment the user is in. In our example, one way we could reduce render times is to optimize the size of the JavaScript files we're loading. Techniques like minification and tree shaking can help with this and should reduce the overall script download times. So this is definitely an improvement, but it's still not great. The recipe said to ensure that nothing is blocking rendering after the LCP resource finishes loading. It doesn't just say to reduce the blocking time. In this example, the JavaScript code contains a framework that is client-side rendering the application. So if we update our framework to use server-side rendering, or to pre-render these pages as static files, then the JavaScript will still load, but it will no longer be a bottleneck for rendering the LCP image. That's much better. Now the JavaScript code isn't blocking rendering at all, so the LCP image can render as soon as it's downloaded. Step 3 in this recipe is to reduce the resource load time as much as possible, and you can do that by following all the general best practices around optimizing images and web fonts. Anything that you can do to reduce the file size of the resource should reduce its load times. You should also make sure that you're setting the proper caching headers and using a CDN so that you can serve those resources from a location as geographically close to your users as possible. If we reduce load times in this example, the results would look like this. So we're almost there, but as you can see, there's now a style sheet that's taking a bit longer to download than the LCP image resource. We were actually able to optimize the LCP resource by so much that it's now smaller than the style sheet, which means the style sheet is blocking rendering until it's done loading. I recommend looking at techniques like critical CSS, or you could find other ways to remove the unused styles wherever possible. Another option is to inline the CSS into the document, but that can have negative performance effects for repeat visitors. My recommendation is not necessarily to remove or inline the style sheets, but to just reduce them so they're smaller in size than your LCP resource. That should help ensure that it's either not blocking or rarely blocking, which is a pretty good compromise. In this case, reducing the size of the style sheet slightly is enough to prevent it from blocking rendering of the LCP image, which is good enough to move on to the final step. Step 4 is to reduce your time to first byte. This step is saved for last because it's usually the step that developers have the least control over. It's also one of the hardest to optimize. That being said, having a good time to first byte is critical because it affects everything that comes after it. One of the best ways to improve your time to first byte is to use a CDN. Just like with optimizing resource load times, it's important to get your servers as close to your users as possible. Here's what that looks like. As I said before, any improvements to this part will directly affect every other part that follows. That's because nothing can happen on the front end until the back end delivers that first byte of the response. So, to recap, here are the 4 steps in the recipe. Step 1. Ensure the LCP resource starts loading as early as possible. Step 2. Ensure the LCP element can render as soon as its resource finishes loading. Step 3. Reduce the load time of the LCP resource as much as you can without sacrificing quality. And step 4. Deliver the initial HTML document as fast as possible. If you're able to follow these 4 steps in your pages, then you should feel confident that you're delivering an optimal loading experience to your users, and you should see that reflected in your real-world LCP scores. So now I want to go through a real-life example of actually applying this to a real web page. So here I have a demo page that I created to mimic a lot of the real-world issues I've seen recently on sites that are trying to optimize their LCP. The demo includes a photo slideshow viewer that consists of a main image as well as several image thumbnails. This type of pattern is common across the web on everything from news sites to e-commerce sites to general landing pages. The demo also loads 2 web fonts as well as the CSS framework, in this case Bootstrap, because these types of dependencies are also common on the web, and I wanted the demo to be reasonably realistic. Okay, let's head over to the code. And the first thing I want to show you before we start optimizing is I added a file called perf.js that my demo is loading. This file calculates the 4 LCP subpart timings and logs them to the console. It also uses the performance.measure method from the user timing API so that I can easily visualize these timings in DevTools. Let me open up DevTools to the Performance tab and show you a quick trace so you can see what I mean. So as this page loads, I want you to notice that the text comes in first, and then you can see a gap where the photos will go, and then eventually all the photos fade in together, once they've all finished loading. Now that the load is done, take a look at the LCP subpart timings here in the timings track. I've staggered these timings so that the TTFB and the resource load time are on the top row, and then the resource load delay and element render delay timings are on the bottom row. Remember that the goal is to be spending about 80% of your time loading the main document and the LCP resource, which are the 2 timings here on the top row, and then less than 20% of your time in the load or render delay portions, which are here on the bottom row. As you can see from this trace, we're spending most of our time in the resource load delay portion, which is a problem, so let's fix that. But before we switch to the code editor, let's take a closer look at the network waterfall to see what's happening within the resource load delay portion of LCP. As you can see here, we're loading a few fonts and style sheets. Once that's done, we have some JavaScript files, and once the main.js file finishes loading, there's an API request for photos.json. The LCP image doesn't start loading until this API request finishes. So if we want to reduce the resource load delay, then we have to start loading the LCP image resource earlier. And the two methods for doing that are preload or priority hints. But given that the load of this image was not initiated from the HTML, it was initiated from the JavaScript, then that limits our options to really just preload at this point. To preload your LCP image, you can add a link rel preload tag to the head of your HTML document, and you set the href value to point to your image URL. Also make sure to set the as attribute to image. Now the image resource is discoverable from within the HTML source, so the browser doesn't have to wait for the JavaScript and API request to finish before it can start loading the LCP image. Let's take a look at how that improves things. So you can see that the LCP image now started loading earlier, but it's still not loading as early as the fonts and style sheets, which means we have more work to do here. The reason it's starting later than those other resources is because Chrome is assigning it a low priority, which it generally does for images that aren't in the viewport. And these images actually aren't in the viewport because the JavaScript code that puts them there hasn't run yet. One hack to get Chrome to load this earlier is to move our link rel preload tag above all the other link tags. But that doesn't really address the priority issue. A better, more semantic option is to use the new priority hints API and just tell the browser that this request should be high priority, which we can do with the fetch priority attribute. Now that we've added that, let's run the trace again to see the difference. As you can see here, the image now starts loading at the same time as the other resources, and it's assigned a high priority. Also, notice that the resource load delay segment is now tiny, so our job here is done. Let's move on to step 2 and address this long element render delay. If you remember from earlier, I said that the image viewer component was built and rendered in JavaScript, and that it programmatically waits for all images to finish loading before fading in. When the network is fast, this is a nice UX touch, but when the network is slow, it's painful to wait this long before you see anything. So let's fix that. Most popular JavaScript frameworks today support a feature called server-side rendering, which essentially just means that your client-side code can be run on the server so that the HTML that's delivered already has the markup in it when the browser receives it. This is a great solution for pages like this one because it means that the browser doesn't have to wait for the JavaScript to finish loading before it can render the images. Now, explaining how to enable server-side rendering in your application is a bit outside of the scope of this demo, but we can easily mimic the results of what server-side rendering would give us by just copying the client-side rendered code and pasting it into our index.html file. After all, it doesn't really matter what stack we're using. From the browser's point of view, all that's relevant here is that the image element is contained within the HTML response received from the server, and a static file is just as valid of a way to do that as a server-generated response. Now when we reload this page, notice how the images are being rendered as soon as they're loaded, rather than waiting for everything to load and render all at once. And if we look at the timing values here in DevTools, you can see that the element render time segment is now also tiny. So let's move on to step 3 and see what we can do to reduce the load time of the LCP image. If we switch over to the Elements panel and take a closer look at this image, you can see that it's a JPEG, which is not the most optimal format we could use here. And it's also loading a file that's 1600 pixels wide, despite the fact that the rendered size is only 372 pixels, which even on a 2 DPR display is still more than twice as big as it needs to be. So let's address both of these issues. We can convert these files to a more optimal image format like AVIF or WebP, and we can also create a few different sized versions of each of them. Image conversion tools are going to be your best friend during this step. And in my case, I'm going to use the Squoosh CLI to do the conversion in bulk. If we head over to the terminal, I can resize and convert all of my source images to AVIF with just this one command. And if I repeat this process a few times for each of the formats and sizes I want, then in just a few minutes, I can have optimized versions of each of my images in a variety of formats and sizes. In this case, I created AVIF, WebP, and JPEG versions of each at 1600 pixels wide to target desktop and 800 pixels wide to target mobile screen sizes. I could create more sizes if I wanted to, but at some point there's going to be a trade-off between file size savings and cache hit rate on your CDN edge nodes. So now that we have multiple versions of each image, let's update our HTML to conditionally load the best version given the user's browser's capabilities and screen size. We can use the picture element to do that. The picture element allows us to list several source options, and then the browser will automatically pick the best option for us. In this case, I'll list the source files for the AVIF version first because those ended up having the smallest file size. Next, I'll list the WebP source files, and then finally, I'll keep the image tag with the JPEG, since JPEG is supported by pretty much every browser. With this change, let's reload our page and take a look at the trace. Notice how now our resource load delay got big again. And if you look at the waterfall above, you can see that the reason is because we didn't update our link rel preload tag to match the image loaded by our picture element. So we're preloading a JPEG, but then ultimately rendering an AVIF image, which is not good because now we're loading two images. But this raises an interesting question. Is it even possible to conditionally preload the same image that will eventually be used by the picture element? Well, the answer is yes and no. The link rel preload tag does take an image source set attribute, which has all the capabilities of the source set attribute on the image tag. But it doesn't allow you to specify multiple different formats, each with their own separate source sets like you can with a picture tag. Fortunately though, Priority Hints provides a solution here as well. Rather than use the link rel preload tag, we can apply the fetch priority attribute directly to the image tag, and then the browser will automatically determine the right version of the image to prioritize. Like this. So not only is it cleaner to do it this way, but in many cases, developers may not have the ability to modify the content of the head tag just on specific pages, but they probably do have the ability to modify their image tag attributes. So now when we reload and look at the trace, you can see that the AVIF version is being prioritized, and it's also the 800 pixel wide file that's being loaded. At this point, all the remaining optimizations are going to be done on the server side. We'll want to make sure that we're applying the proper caching headers to our images as well as to our HTML document responses to ensure that they can be cached when appropriate. Note that we want to ensure that they're being cached by both the browser, which helps with repeat visits from the same user, but also on the CDN, which helps all users in the same geographic region who may be requesting many of those same resources. In the interest of time, I'm not going to cover those optimizations in this demo. And honestly, any optimizations you're making to your server, CDN, or to your network configurations should be based on real user performance data, not lab-based simulations like we've been looking at here today. So much of your server-side, CDN, and network performance depends on factors like cache hit rate and other things that are directly related to user behavior, which is why you need real user performance data to effectively optimize them. If you want to learn more about measuring and optimizing performance with real user performance data from the field, head on over to web.dev where you'll find lots of resources on that topic. So that's it for me today. If you want to learn more, make sure to check out web.dev/optimize-LCP. It goes into a lot more details on all of the techniques that I covered today. As always, thanks for watching and happy optimizing.